Okay, so what is a cation?
A positively charged ion.
Okay, and an anion?
Negatively charged. Yeah.
Okay, good, good. Okay, so then in the case of a cation, let's see, share my screen. Let's say we have this guy. So what would be the Lewis dot structure? I mean, not the Lewis dot structure. What would be the electron configuration for this guy? Calcium 2+ ion. The calcium ion. Anyone?
Would it just be AR?
That is correct. It would just be AR. So normally, if it was calcium, it would have been our core, noble gas, which is AR, and then 4s2. But we're losing 2 electrons. Since we're losing 2 electrons, we're just left with that core, right? So this tells me that calcium 2+ has the same number of electrons as argon. So we would say these guys are considered to be isoelectronic. Isoelectronic meaning what?
Same electrons.
Same electrons, right? So who else would be isoelectronic with calcium 2, with argon? Like I'm smoking.
All of the noble gases?
All of the noble gases? So you're telling me that all of the noble gases have the same number of electrons.
Would it be F negative, I guess? Wait, argon or, yeah,
Argon.
Cl negative?
Cl negative.
Yeah.
Cl negative.
Be the same as argon.
Would be the same number of electrons as argon. Yes, that's true. Who else?
S. Negative. 2 negative, I guess.
2 negative.
So why is the number in front of the negative and positive sign?
Because it lets us know that, well, it depends on the text, but most texts will actually write it with a number in front. It lets us know that we have 2 electrons here, right? So it's kind of reminding you that you have 2 electrons that are being added here. And then here, this reminds me that I have 2 electrons being removed.
Okay.
Okay, so those guys are all considered to be isoelectronic to argon, meaning that they have the same number of electrons as argon. Now, again, the reason why you want to be a noble gas or be like a noble gas is why?
Because they're stable.
Because they're stable, right? So at the end of the day, it's about stability. You want to try to find a way of being stable. Like I talked to you guys about your lives. The reason why you're taking this class is because you're looking to try to get stability in your life. You want a stable paycheck coming in, right? You want to make that money, right? Yes, no, maybe?
Yeah.
Yeah. Okay. So we want stability. That is the reason why we do the things that we do. So that is exactly why these atoms become ions, because they want stability, right? And so they try to find the best way of remaining stable, right? Okay, so you guys have a clear understanding of what isoelectronic means?
Yes, sir.
And you have a clear understanding how to write Lewis dot structures?
You use the valence electrons, correct?
Yes, you're going to use the valence electrons. So in the case of, let's go back to that calcium. We know that calcium had how many valence electrons?
2.
It had 2 valence electrons because that core, right? We don't want to touch that core. We want to leave it alone. We know that it had 2 electrons that we could actually work with. Okay, so we would write our Lewis dot structure this way. So if we were talking about the calcium ion, we'd put it in brackets. It would have no dots, and we put the 2 plus to let us know that we removed those 2 electrons. Okay, questions, concerns, Cash? Good. Okay, so we know that this would be how we would write the fluoride ion. This would be the sodium ion. And when they come together, we know that they're going to form our sodium fluoride, because of the 2 charges are able to sit there and interact with it, right? What type of bond is this? When 2 ions are coming together.
An ionic bond?
Ionic bond. Okay, so we know that this is an ionic bond because you have the 2 ions that are coming together, right? So the best way of remembering that is you have a metal and a non-metal. The way that they're going to interact is going to be ionically, right? So they're going to form ions, and then they'll be able to interact by their charges, that plus and that minus.
I have a question. How do you know which one to put in the front and which one to put second? I always had trouble with that.
So always think of it as you always want the good news first, right? Positive first, right? Tell me the good news first, and then tell me I'm dying, right? Say I won $1 million, but you're dying of cancer. Hey, that's perfect. I have $1 million to go and spend before I die of cancer. Give me the good news first. Good news first. Positive always comes first.
Oh, okay. Thank you.
Okay. Okay, piece of cake. So you know what an ionic bond is. So let's talk a little bit about ionic bonds. This. Or that's what you're sharing. Okay. So this here, this table, did I show you guys this table? I can't remember what I showed you because it all starts blending together. Well, I'm going to show you now. So when we talked about isoelectronic, these guys are all isoelectronic with neon. Okay, so we had nitrogen. So N3 minus is isoelectronic with neon. It has the same electron configuration as neon, which is 1s2, 2s2, 2p6. Here's neon, exactly the same electron configuration. Fluorine minus, right? F minus, 1s2, 2s2, 2p6. O2 minus, 1s2, 2s2, 2p6. So all of these are examples of monoatomic ions that are isoelectronic with neon. These guys are all cations that are isoelectronic with neon. They're also monoatomic. Okay, so sodium, 1s2, 2s2, 2p6. Magnesium, 2 plus, 1s2, 2s2, 2p6. And aluminum, 3 plus, 1s2, 2s2, 2p6. Okay, so in all of these cases, here's the Lewis dot structures of the original atoms. When they're lost, they just become this, and you want to put the brackets around them, even though I was lazy and didn't put them on the table. Okay, so this just basically shows us by color coordination. Anybody colorblind? Which ones are isoelectronic with each other? So H minus is isoelectronic with helium. Lithium plus is also isoelectronic with helium, meaning that they have the same electron configuration as helium. The ones in blue, we just talked about, all of those are isoelectronic with neon. The ones in yellow, all isoelectronic with argon. Piece of cake, simple. Okay. So we've already done the example for calcium and ionic compounds. Okay, so we talked about ionic compounds, the fact that they're going to be attracted to each other by the opposite forces. So we have that positive and that negative. They're going to come together, right? So what's going to happen in reality is that they're going to form what we call a crystalline lattice. And I'll show you a picture of that in a second. So you have one that'll be a plus, and then the one that'll be a minus. And that one that's a minus is going to surround that plus, because that whole thing is positively charged. So it has this aura of positivity around it, and each of the negatives are going to be attaching to it. So like if I have a magnet, right? And then I have 4 other magnets around it. What happens? Are those magnets going to pull towards it? Or is only one of them just going to attach to it and that's going to be it?
They would all start getting close to it.
They will all start being pulled towards it, right? And that's exactly what happens with that positive and negative charge. If you have something that's positively charged in the middle, all your negative charges are going to try to surround that, okay? So there are a couple of things that we need to know about ionic compounds. One of the things that we need to know is that they're pretty strong bonds, right? Long as there's nothing that's going to disrupt that positive and negative charge, it's going to be really hard to dissociate. They're also, at room temperature, mostly solids. So ionic compounds are almost always solids at room temperature. And then the last thing is that when we put them in water, ionic compounds, in most cases, they're going to be good conductor of electricity. Or if we melt them and disrupt those bondings, they're also going to be good conductor of electricity. Why do you think if we melt it and it kind of disrupt that bond, why is it going to be good at conducting electricity? Or if it's in water? Anybody want to take a guess? Anyone? Jason, come on, you gotta take a guess.
I don't even have any decent guess.
So if I'm putting it in water and I'm disrupting that positive and negative charge, that attraction, so what does that do? Is that allowing us, what's happening? What is electricity, first off? I'm just curious. What do you guys think electricity is? Anybody want to take a guess? Electricity. Let me spell it for you. Maybe that'll help. Let's annotate. Electricity, right? Electricity. Man, that word looks so damn
Is
familiar.
it a movement of electrons?
Oh my gosh, that is so right, Jason. Good job. It is
The flow of
movement
electrons. Sorry, that's the actual definition.
That is the actual definition. the movement of electrons. Electricity is just the movement of electrons. That's how we get light. Let there be light. Okay, so if electricity is the movement of electrons moving, how are you going to be affecting those electrons moving if you have some positive and negative charges in there?
Can you repeat the question?
I said, if electrons are moving, how do you think having positive and negative charges in a solution is going to affect that?
It's gonna disrupt the flow of it.
Is it? So if I have, let's say them together, right? The positive and negative charge together, and I have an electron coming towards it, is that going to affect it at all if they're connected?
No.
It isn't. It's actually going to stop. It's not going to do anything, right? So if I have a bowl of salt, just solid salt, and I stick 2 jumper cables in there, right? One that's going to be that positive flow and one that's going to be a negative flow on opposite sides. Is anything going to happen? Is my battery all of a sudden going to start up?
I don't think so.
No.
Let me give you a hint. How many of you guys, I should say, my car has this issue. There are certain batteries, the brand of batteries that I always get, unfortunately, I am a cheapskate. I'm not gonna lie. And so I learned when I got the cheap battery, I would get a salt crystalline structure on the top of the jumper, right? And my battery would never start up. I'd be like trying to get it to start. Why wouldn't it start? Why? You guys know exactly what I'm talking about? That buildup
Yeah.
of salt on the top of the battery?
Yeah.
Yeah, that blue stuff.
Yeah, why wouldn't it start? Why?
Because it's stopping the flow of the electrons.
Because it's stopping the flow of the electrons. Even though it's salt, there's positive and negative charges, but they're connected, right? They're balanced out. They're neutral. So there's no free charge to sit there and exchange that electron with, right? Because that's all it is the flow of electrons. So if I have a positive charge to interact with that negative charge, I can just get this pattern of flow of electrons through that solution. So if they're free to interact, I can get that flow going, right? So if it's in a liquid solution where I have a free sodium, did I talk to you guys about water being a home wrecker? Did I ever mention that to you?
I don't think so.
You don't think so? Let me show you this now.
Doesn't sound familiar.
I think we did, but you know, it's like I say a lot of things, and sometimes you guys are like, what am I gonna have for dinner? Ooh, he's got a cute butt. Or, you know, you're always thinking about so many other things, right? So when we talk about water, water has what we call a dipole characteristic, meaning that it is partially positive and partially negative. So the electrons will spend more time with oxygen than they'll spend with hydrogen. So that means that this guy is called what we call partially negative, and this guy is partially positive, right? Since it's called, we call it a dipole moment, meaning my electron is spending more time with oxygen because oxygen is much stronger. It's pulling the electron towards it because oxygen has a stronger electronegativity. Since that's the case, and we'll talk a little bit more about electronegativity here in a second, oxygen is like, hey, I need the electron more. I'm more of need. I'm a little stronger than you, so I'm going to keep it on my side. I talked to you guys about sharing evenly and unevenly. I did talk to you about that. So this is that example of that sharing evenly and unevenly. Remember, me being the bigger brother, right? I take the Atari from my sisters and I play with it all day. And then right before my mom gets home from work, I give it to my sisters. So then they could say that they play with it. And then when my mom comes in, I'll be like, oh, it's my turn now, you know, and start playing with it again, right? So I had a really good system going on, okay? So I
That's
got
so
the Atari,
mean.
It sounds like something you probably actually did, huh?
Hey, one of the perks of being the older brother, right?
Oh my goodness.
So in that case, oxygen was kind of like me. It gets the electron the majority of the time. my sisters were kind of like hydrogen. They only get the electron a little bit at a time. So that sets up a dystopia, right? So I'm getting it, I'm more negative because the electron is on my side a large part of the time, and my sisters would be more positive, you know, in that case, or hydrogen would be more positive. Okay, so because of that, these guys are what we call partially negative and partially positive, where sodium is completely negative. I mean, completely positive, sorry, because it's giving up that electron. And chlorine is completely negative. So sodium completely positive, chlorine completely negative. Who is oxygen going to interact with, since it's partially? Negative.
Would it be chlorine?
It's sodium.
It's going to be sodium, right? Because sodium is a positive charge. Oxygen has this partial negative charge. What is that? Opposites attract, right?
Yeah.
Okay, so you're going to have what we call a weak interaction between that sodium and that oxygen. It's a weaker interaction. Right?
So that's only because of the two hydrogen atoms that are connected to it. So if it wasn't connected to it, it would connect to chlorine?
No, because remember, oxygen, when it has the opportunity, is it going to want to be negative? Think about it. Is it going to want to be like a noble gas? If it's going to be like a noble gas, what does it have to do?
Oh, yeah. It has to gain electrons.
It has to gain electrons.
Okay.
So it's going to do whatever it can. You know, it'll share electrons, but long as it gets the electrons majority with itself, right?
Yeah.
The only person that it will buckle to is somebody who has a stronger electronegativity, and we'll talk about that. And the only person that does that on the periodic table is fluorine. Fluorine is like the ultimate bully. Okay, and we'll talk about him a little bit later.
Okay, thank you. Appreciate it. Makes sense.
Okay, so fluorine, so the hydrogen is going to interact with the chlorine. Okay, because that chlorine is negative. So positive interacts with negative, right? We all know that. Opposites attract. You can't tell me you guys all had gone through this in high school where you're in love with that bad boy, right? Because I'm assuming that you guys are all good, the good kids, right? And you're like, oh, you come home, mama, you know, I met the most beautiful guy ever. You know, he's so beautiful. And your mom, who was it? Oh, it was Johnny Blah, right? Johnny Blah, that Blah family, they are dirty dogs. They are horrible. You're not allowed to touch that boy. Get away from that boy. He is bad. He's just going to get you in trouble. And what did you do? Kristen, what did you do? I know you're one of them. What did you do, Kristen?
Okay, I guess I'm just gonna bypass that accusatory statement there, but but you go ahead and date him anyways, you know, because you're attracted to him. So
Exactly. You go ahead and date him anyways because he's the bad boy, right? Opposites attract. You're the good girl. He's the bad boy, right? And so you guys get together and you're like this. So in love, right? Now, see, the thing is, because your opposites attract, water takes advantage of that in a sense. Because water swings both ways. It goes to Kristen, says, hey, Kristen, you don't need Johnny Blah. You got me. I'm water, right? I can make you happy. And then as soon as Kristen turns her back, water goes to Johnny Blah. Honey, you don't need Kristen. You got me. Right? I can make you happy. And so water separates the two. Right? So water's that home wrecker. Okay? Because it has both of those charges, right? Or those partial charges, it's what we call dipolar, meaning it has two poles. It has that plus and that minus. It's able to swing both ways. Okay? By interacting both with that positive charge and that negative charge. So that's one of the best characteristics of water. That's why water is the ultimate solvent, right? Because it's able to do that. Okay? Okay, are we good? You guys got that? You understand it?
Much better now. Thank you.
Yeah.
No problem. Okay, so now since you have these in solution, right? You have this positive and that negative, whole positives and whole negatives in solution, not partial positive and partial negatives, right? Electricity is able to flow through because it'll start interacting with that plus. And then that'll kind of shift this minus to push along. And then, so it'll get a flow of those electrons through that solution by that interaction, like a little table, like domino set, right? You hit one, hit the other one, until it hits the other metal post, okay? And I'll show you an image of it in a second. So this happens when we're in an aqueous solution or in a water solution, or when we melt that ionic compound. So this basically just showing you sodium and chlorine, sodium metal, and with chlorine gas, it forms this really huge, violent reaction because both of them are very anxious. Sodium is anxious to get rid of an electron, chlorine is anxious to gain an electron, right? And because of that, the reaction is going to be pretty violent, right? So this is just basically showing you that reaction where sodium gives up its electron to chlorine. So then chlorine becomes the minus chloride ion, negatively charged chlorine ion. And then sodium, the sodium ion, positively charged. It loses that electron. Now, because you have that plus and you have that minus, those guys are going to interact, forming this lattice. And so here, the gray represents the sodium ion, the green represents the chlorine ion. Now, if you look around it, that sodium ion is surrounded by those green, right? And vice versa. Okay? You guys see that?
Yes, see it.
And so that's how we get this beautiful salt crystal by these two atoms interacting solely on electrical charges, that plus and that minus charge. Okay, this is just another image of the ball and stick model of the lattice itself. This is just the space filling model of the same lattice. And this shows you the 3D structure where you can see, you know, visibly through the ion. So you can see that the sodium ion is over there, and it's over here, and it's over there. And so you get this nice organization in that crystal lattice. Okay, this is just showing you when we melt salt, and you can melt salt, it takes a lot of heat, a whole lot of heat. But as soon as you melt salt, it breaks up those interactions, right? And it allows electricity to actually flow through as a result of that. So it will conduct electricity when it's melted or it's in its liquid state, okay? Or if we just put in water, okay? Questions, concerns, Cash?
So would that statement be true for any ionic compound in its liquid state?
Yes, that would be true for any ionic compound in its liquid state. However, some ionic compounds take a whole lot of energy to sit there and break or disrupt those bonds, right? And it varies from ionic compound to ionic compound. For instance, how many of you guys seen rubies? A ruby. So ruby is aluminum oxide. And so, you know how you get rubies of different colors and everything like that? So a ruby of different colors, like for instance, if you want the redness of the color, so it has sprinkling of manganese in it. So that'll give you a red ruby. Where if you have copper in with aluminum oxide, just sprinkling of copper, that's going to give you like a bluish, greenish color ruby. So just depending on what you sprinkle it with, it's going to be a different one. Now, a ruby, aluminum oxide, is going to be a lot harder to melt. It's going to take a lot of energy to melt a ruby compared to melting sodium chloride. Okay, because of the charges that are involved. Aluminum has Al3 plus and O2 to sit there and kind of keep it stabilized, whereas sodium chloride is just aluminum. Aluminum oxide. So aluminum is Al3 plus, and the oxides are going to be 2 minuses. And so you're going to need 3 of these guys and 2 of these guys to balance each other out. And that's what I'm just basically saying here. Now, because of those charges are so much higher than, let's say, sodium chloride, Na plus Cl minus, which only has 1 plus and 1 minus, these guys, 3 plus, 2 minus, right? This guy is going to take more energy to sit there and melt than this guy would. Okay? That's just a little extra for you. Okay? So covalent bonds are sharing of electrons, right? Now I talked to you about how water is sharing of electrons. So there's 2 ways to share, right? One is evenly and one is unevenly. The way I shared with my sisters, is that even sharing? Oh, you get it part of the time, I get it part of the time, and we go back and forth. You get an hour, I get an hour. You get an hour, I get an hour. Is that even sharing? Okay.
Yeah, that would be.
Or in the case of me, where I would spend all of the day when my mom was at work playing a video game, and then my sister gets it for about an hour, and then I take it back again from as soon as my mom gets off of work and play the video game. Is that even sharing or uneven sharing?
Uneven.
Uneven, okay? So if it's even sharing, it's called nonpolar. Covalent bond. And then if it's uneven sharing, it's called polar covalent bonds. Good? Piece of cake?
Can you repeat which one was which? Because you wrote, it looks like you wrote even on both.
Oops, uneven. There we go. Thank you. I did write even on both. Thank you for correcting me. I was just trying to keep you on your toes, Kevin.
So
Okay.
would the nonpolar and polar bonds only be relevant to covalent bonds, not like ionic bonds or any
That's
other
right.
ones?
That is correct, Jennifer. It's only relevant to covalent bonds. So you only have 2 types of covalent bonds, right? Either they're polar or they're going to be nonpolar. Okay? So water was an example of polar or nonpolar.
Sorry, what was the question?
Water is an example of a polar covalent bond or a nonpolar covalent bond.
Polar.
Polar.
That is correct. Okay. So hydrogen interacting with itself, because they're going to be even to each other, they're like twins. Twins that are the exact same weight, that are the exact same size, they work out exactly the same. They're going to have the same strength, right? So is that going to be a polar covalent bond or a non-polar covalent bond? Is either one of the twins going to be able to pull the electron more than the other if they're exactly the same?
And it'd be
Nonpolar.
nonpolar.
It's going to be nonpolar, okay? So when we're talking about the formation of molecules together, we often are going to be using the Lewis dot structure. So this is the Lewis dot structure for hydrogen, one hydrogen. This is the Lewis dot structure of that other hydrogen. Now, for hydrogen to reach its quote octet, or to reach its happy state, it needs to be like helium. Helium has a total of how many electrons?
2.
2. So hydrogen has one valence electron. Each hydrogen has one valence electron. So it's going to share those 2 electrons. So it's like helium. So the way that we represent sharing of electrons, we draw what we call a bond, right? And that's just a line between the 2. So these guys form a covalent bond between each of the hydrogens. So that means it's sharing 2 electrons. You guys see that? Okay, so if something is sharing more than 2 electrons, let's say it's sharing 4 electrons. Let's do this. I'll make you work for it, instead of just giving it to you. How many valence electrons does oxygen have? You want me to show you the
6.
quick way of determining? It has 6. Did I show you the quick way of determining? Let me
No,
show
I
you the
don't
quick way
think
of determining.
so.
Okay, let me pull up my P table. You guys all see the periodic table?
Yes.
Yeah.
Okay, the easiest way to determine the number of valence electrons is just counting the s and the p orbital at the period that element is at. So oxygen is at what period?
The
2.
second period.
Second period. So then just count 1, 2, 3, 4, 5, 6 until you get to that element. So it has how many valence electrons?
6.
6.
1, 2, 3, 4, 5, 6. So carbon has how many valence electrons?
4.
4.
Okay. 1, 2, 3, 4. What about arsenic?
5.
1, 2, 3, 4, 5. Piece of cake? Okay, so let's go back to. So let's talk about oxygen. So oxygen, we know is diatomic. So if I'm saying O2, how many valence electrons does each of those oxygens have?
6 each.
6 each. So we have 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4, 5, 6. Okay. Oops. Okay. So noble gases, let's say neon. How many valence electrons does neon have? If I do the counting method, or how many electrons does valence electrons does neon have overall in that outer shell? Just the N and the P.
8.
8. So the goal of most chemical compounds is to try to get so that you have 8 electrons around every atom. Okay, so like we were talking about, hydrogen needed 2 because they wanted to be like helium, right? So we had H. So this guy has 2 around it, this guy has 2 around it. Okay, so both of those guys are happy because they're sharing those 2 electrons. So we need to find a way of making it so that oxygen has 8 surrounding each of the oxygens. And so we're going to share, because these are 2 non-metals coming together, we're going to be sharing electrons, okay? So how many electrons are going to need to be shared so that each of these guys would have 8 around them?
2.
Just 2? So if I put these 2 over here in the middle, so then that'll give me O dot 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 dot. And then I have the 2 that's here. And then this guy would have 2, 4,
Oh,
6.
so then would it be 4?
All right, so it needs 4. So we need to bring another 2 over. So let's do that. Now we've got to remember that electrons are mobile. So if electrons are mobile, they're basically able to move around, right? So that's 2, 4, 6, 8 around this oxygen. And that's 2, 4, 6, 8 around that oxygen. So it's happy, right? Because the octet is full. So each of those oxygens, they feel like they're just like neon. Okay? Piece of cake? So this would be, oh, go ahead.
Each line represents 2 electrons, basically?
That's right. Each line
Okay.
represents 2 electrons. This would be called a double bond. This guy over here was a single bond, right? Double bond means that you're sharing 4 electrons. Okay, what about nitrogen? Let's do nitrogen. How many valence electrons? Because we know that nitrogen is also diatomic, right? We're going to do N2. So how many valence electrons does nitrogen have?
5.
1, 2, 3, 4, 5. And so this guy is also going to have the same number, 2, 3, 4, 5. Okay, so what do I need to do to make both of these guys happy so that they have 8 electrons around each one of them?
You just share 6 electrons?
So they're going to be sharing 6 electrons. I'm going to take these 2. Okay, so that's 2, 4, 6, 8 around this nitrogen, 2, 4, 6, 8 around this nitrogen. So in that case, both of them are happy. Okay, so this,
I have a question.
yes,
Why is there 3 lines when you only circled 2?
because we have the one over
Like
here
pairs.
between the 2.
Oh, okay. Perfect. Thank you.
Okay, so the goal is, again, if you can, you want to try to have 8 around you so that you'll be like a noble gas. Okay, now there are going to be exceptions to this. There's always exceptions. Welcome to chemistry. There's going to be an exception, right? Okay, how are you feeling so far? Pretty easy?
Yeah.
Okay, so I'm going to give you guys a couple of compounds that I want you guys to work as groups to do Lewis dot structures for it. What time is it? How we're doing on time? I got 15 minutes. Perfect. That's just like I give you 10 minutes to get it, and then 5 minutes we can talk about it. How about that? Are you guys ready?
Yeah.
I want to hear excitement. I want to hear you guys scream that you're ready. Come on, Vanessa. Tell me. Are you ready? You ready, Vanessa? One of these days, it's going to work. I keep hoping. Okay, so you guys are going to do, here's the first one. You're going to do F2. Let's do CO. And you're going to do N2O. And I'm going to give you a hint when you have stuff that has 3 in the middle. So I'm going to give you a quick way of determining it, and then I'm going to give you a more complicated way a little bit later. But the guy who is the furthest away from a noble gas always gets put in the middle. Okay? And we'll do CO2. Okay? Are you guys good? Those 4?
Yeah.
Okay, so let me make you break out rooms real quick. Let's see. Okay. Boy, people were jumping ship real fast. Could have sworn we had more people than this. I think that's good. Okay, rooms are open. Do we have some answers?
Yeah.
I know a few of you guys have class, so we'll be real quick. The other group didn't want to come back. Okay, so everybody's back now. Okay, so let's talk about fluorine. How many valence electrons does each of the fluorines have?
7.
Okay, how many are they going to share so that they have 8 around them?
They're each going to share 1. So they're going to share 2 total.
Okay, 2 total, so that's 2, 4, 6, 8. 2, 4, 6, 8. Piece of cake?
For that one.
Yeah,
Okay.
that one's easy.
Now let's look at CO. How many valence electrons does oxygen have?
6.
6.
Okay, so let's see. 1, 2, 3, 4, 5, 6. And carbon?
4.
4.
1, 2, 3, 4. Okay, so how many are these guys going to have to share so that both have 8 around them?
Are they
Would
gonna
it
have?
be
Sorry.
6
Oh,
total.
go ahead.
Yeah, I was gonna say 6.
They're going to have to share 6. Okay. So we'll get, then of course, these 2 here. So we'll get triple bond. Okay. Piece of cake.
Yep.
Now what about C? Oh. I'm going to assume they have the same number of valence electrons as the last one.
Yeah.
Okay? So how many are you going to share on this side, and how many are you going to share on this side?
Is there 4 and 4? So 4 for each side, so you'll have double bonds.
Right. And then, of course, we have the 2 here. So then we get piece of cake.
Yes.
Okay. And then the last one. Let's put it down here. We have N. Who's going to be in the middle?